Okay, let's get started. Okay, class, as you all know, next week is the midterm, next Thursday, so I had a few announcements to make. First of all, visit the website. There's some information that may be useful to you. One of it is that I'm going to have extended office hours on Tuesday from 1:30 to 3:30, but they're not really extended, they're more like makeup office hours because I'm not going to be here Wednesday and Thursday. So if you have questions about the exam, lecture, homework, please come to Tuesday's session. There's also a sample midterm that I've posted. It's actually last year's midterm exam, so you get an idea of what the midterm may look like this year. And finally, for those of you who still don't know, the midterm will not be in this room. It's going to be held in 126 Barrows during the regular classroom time. Okay? And that's all on the website. Okay, questions or comments? And basically, today's lecture is the last lecture for the midterm, so you're responsible for all the material, including today. The next lecture, what I'll do is I'll go through the sample midterm with you guys, and maybe if there's time for some more sample problems we can solve together, and then you'll have the midterm. Okay? All right, so if you remember last lecture, we're looking at the MOSFET device as an LNA. And we basically calculated the noise figure, and what I'd like to do today is revisit that, and in particular, calculate the F-min for the device. And then we're also going to look at the matching problem for a common source device. And then the solution will be to use inductive degeneration. So we'll spend quite a bit of time talking about an inductively degenerated MOS amplifier. Okay? So let's recap the calculation of the noise figure. So if I draw the simplified equivalent circuit, we're going to include the drain noise, CGS, let's call this V pi, GM V pi. This is our gate, which generates a noise. And then finally we have our noise source and our source resistance. Okay? And I'd like to just recalculate the noise figure of this, making the observation that the output current, let's say I out, is some capital GM of the source voltage. Okay? So I want to calculate that capital GM. Now this is pretty easy to do. If you look at the input of the transistor, a voltage source will generate a current, so I can say that IN is Vs divided by the total resistance in this loop, which is Rs plus Rg plus 1 over j omega CGS. And basically the output current is GM V pi, which is GM over j omega CGS, which is omega t over omega times minus j, times this V pi that we just calculated, which is j omega CGS, 1 plus j omega CGS, Rs plus Rg, times Vs. Okay? So we see this term goes away. And if I assume that I'm at frequencies which are sufficiently high, then this term will dominate over this term 1. And so I'll get GM over j omega CGS, Rs plus Rg, Vs. And of course, you recognize GM over CGS as the omega t of the device. So this is minus j omega t over omega, 1 over Rs plus Rg times Vs. Okay? So this is the current gain of the device, or the transconductance of the device. Basically, a voltage on this side produces a current on this side by capital GM. So it's interesting to see at high frequencies, the GM of the transistor effectively is a ratio of omega t to omega times basically 1 over the source resistance, assuming Rs is bigger than Rg. Okay. Now this way of thinking is going to come in handy later on. And in fact, you can see that it allows us to very quickly calculate the output noise, the total output noise. Total output noise, therefore, is just GM squared Vs plus Vgate plus, if I go back and look here, total output noise is this drain noise plus the current gain, which we've already included. And so this is the drain noise squared. Okay. Any questions? Good. All right, so from this expression I can calculate the noise figure. The noise figure is the total drain current divided by the drain current just due to Rs, which is just this first term here. So that gives me 1 plus Vg squared Vs squared plus I drain squared Gm squared Vs squared. Okay. And just as before, we now substitute 4kTb Rg here, 4kTb Rs here. For the drain noise current, I substitute gamma over alpha Gm. For Gm squared, I substitute basically Rs, 1 over Rs plus Rg, omega over omega t squared. I'm interested in the magnitude, so that goes away. And on the denominator, I have Rs. Okay. Any questions? Okay, now you can see that there's some simplification in order here. In particular, let's assume that Rs is bigger than Rg. Otherwise, we'd have a terrible noise figure, right? So let's assume that we're at least a factor of 5 or 10 bigger than Rg, because we don't want this term to contribute to the noise figure. And so then we have F is 1 plus Rg over Rs, gamma over alpha. Gm, here I have Rs squared, here I have Rs, so I just get Rs, omega over omega t squared. And this is the same expression that we derived last lecture. Okay. Now the question is, first of all, how accurate is this calculation? You know, can anyone think of something we've neglected, something important that we've neglected in this calculation? C mu, that's true. We really have neglected C mu. And there's a good reason why we've neglected C mu. The reason is that it just would make everything messy. Want nice, clean results. No, more seriously, we're going to cascode the device. So later on, when we cascode it, C mu will have a minor role to play. Okay. Otherwise, we definitely would have to include it. Anything else that we've neglected? Source resistance? Oh, you mean the resistance down here? Yeah, that's true. We have neglected that, and that may be important in certain applications. Usually we like the device to be fairly big for the LNA, so the source resistance won't be too large, but certainly something that we could include in the calculation. Good midterm problem. Okay. Anything else? So something should be screaming at you, right? The gate-induced noise, right? We kept making a big deal about the gate-induced noise and the fact that it's correlated to the drain noise. And for the past couple lectures, I've just been ignoring it. Okay? So the reason I can ignore the gate-induced noise is the following. It's actually a very nice, convenient thing that happens. So if I were to include the gate-induced noise, all I would have to do is say Rg has several components. It has a channel resistance, induced channel resistance, plus, let's say, some poly resistance, right? So I've actually carried along this gate-induced noise with me, but I've ignored the fact that it's correlated, right? That's what should be bothering you. Now, if you look in a textbook on the gate-induced noise, especially in Tom Lee's book, they mention that you can represent the gate-induced noise as either a current or a voltage. And if you represent it as a voltage, then what the value of this gate-induced noise is 4kT delta times the intrinsic, let's say, channel resistance. Okay? And the channel resistance is 1 over 5 GM. Okay? And this factor delta is approximately 2 times gamma. Okay, approximately. So 4/3 for a long channel device. Well, the problem with this formulation is that this noise is correlated to the drain noise. So this is GMV pi, and then we have our drain noise. And all the calculations that we've done up to now are invalid because we neglected that correlation. Okay, any questions up to here? Now the nice thing is that if, on the other hand, you assume that this resistance is a white noise of just 4kT R channel, and assume that, so delta, I'm assuming delta is 1, but I'm assuming that this noise is uncorrelated to the drain noise. So this noise is uncorrelated to drain noise. Then you get the right answer, or approximately so. So it turns out that the easy solution gives you the right answer. If you do the hard way and take the correlation into account and everything, you get a slightly more accurate answer, but believe me, it's a lot more painful to arrive at. So this approach is a very nice way of handling the MOS noise, gate-induced noise. You just assume it's uncorrelated and you get rid of this factor delta. Okay? Now that's a subtle point. I think that maybe some of you don't really get it. So I encourage you guys to come to office hours and talk to me about it. This is a more advanced topic. Okay? For those of you who have been exposed to this before, I think you know what I'm talking about. Okay? Any questions about that? Yes?
Sorry, can you briefly explain why that? Why?
Well, what happens is that the part that's correlated kind of cancels out some of the noise. When you actually go through the noise analysis, you find out that because this is correlated to this noise, when you calculate the minimum achievable noise figure, you can cancel out some of the drain noise with the gate noise. And that's why the effective value of the independent noise is smaller by this delta factor. Okay? It's very complicated, actually. There's lots of distributed circuit analysis that you need to do. There's actually papers written on this. This model is known as the Papajewski model. I'm mispronouncing the name. But in the paper, they try to give an argument for why this is true. The argument's not exactly crystal clear, but at the end of the day, you do get good results with this model.
Doesn't the algorithm depend on the topology of the topology, because you get different gains from the channel to you?
Okay, so the question, I'll repeat the question, is doesn't this argument rely on the topology of the transistor? I don't think so, but I'm not sure. As far as I know, in my experience, using this approximation, you get a very good answer. Okay. So I don't want to spend too much time talking about this approximation. I want to get back to getting some results. And in particular, we'd like to find now the minimum achievable noise. And instead of using the two-port theory that we did last lecture, I'm going to do exactly what one of you guys suggested a few lectures back. In fact, it was Amin who said, why not just find the noise figure and then take the derivative with respect to source resistance? So there's the noise figure. If I take the derivative with respect to RS, I get minus RG over RS squared plus, this is all a constant, gamma over alpha, omega over omega t squared, GM. And I set that equal to 0. And now I can solve for RS. That gives me the minimum achievable noise figure. Okay? So I do it. Piece of cake. Wish they were always so easy. The answer is RG divided by gamma over alpha, omega over omega t squared, GM square root. And this is really RS opt. And I can write this as omega t over omega. I can take this out of the square root, and the rest remains. Okay. And now I just substitute this into F to find F min. So F min is 1 plus RG divided by this. plus gamma alpha omega t gm times this expression, omega t over omega. So this cancels out with that, rg gamma over alpha gm. Okay? And if you stare at this expression for a while, you realize that these two terms are actually equal. Right? This is rg divided by this term. I'm dividing here. This is equal to this, right? This divided by square root brings the square root on top. So you do a little bit of algebra, and you'll see that f min is simply 1 plus 2 times omega over omega t gm rg gamma over alpha square root. Okay? So this is a very important equation. Yes, there's a question.
You're solving for, I don't think this works. Well,
It
you're
works.
solving for R opt,
Mm-hmm.
RS opt. Isn't F taken with respect to RS opt equal, or RS equal to 50 ohms? So if you're doing RS opt, then what? Yeah, how does that work with the noise figure?
Okay. So noise figure is a function of source resistance, right? Now usually for a system, when we measure it, we like to measure it with a 50 ohm source as a standard. But not all systems work with 50 ohms, right? If you're in a communication system, you use 50 ohms. If you're in a, let's say, low frequency system, you may prefer to use kilo ohms for your source resistance, right? So the concept of noise figure strictly doesn't depend on source resistance, right? It just, as a concept, noise figure tells me how much is my signal noise ratio deteriorating as I go through a block, right? And it's independent of source resistance. Now in practice, of course, we can't live with an arbitrary source resistance. We usually are given a source resistance. It's like the antenna impedance or the filter that's driving our amplifier's impedance. But we can use impedance matching to transform it to some more optimal value. So here we're saying, what's the best source resistance to drive this amplifier that would give us the minimum noise figure? Okay? And if you interpret this equation, actually, you see that my minimum noise figure is 1 plus, you always have 1, that's the source noise, and then plus this term, which is the noise due to the gate resistance, plus this term, which is the noise due to the drain current. And they're equal, which tells me the optimal condition occurs when the amount of noise contributed from the gate is equal to the amount of noise generated from the drain. So it's an interesting observation. Okay? Let's take an example and plug in some numbers. Okay? So let me take a process that has a 75 gigahertz FT. Right? That would be something like a 0.13 micron process. And let's say we're building a wireless LAN system around 5 gigahertz, right? And let's say experimentally we know that gamma of alpha is about 2. All right? So let's plug into this equation and find out what the minimum noise figure is. Well, the minimum noise figure depends on GM and it depends on RG. And remember, RG has two components. It has the channel component and then the poly material component. And last lecture, we talked about how we could properly lay out the device with multiple fingers to minimize this contribution, the poly contribution. So let's say I really made this small. It's less than an ohm. And so I'm going to neglect it. That's something I have control over by just changing the layout of the device. The channel resistance, though, depends on how I bias my device. It's 1/5, 1 over GM. Okay? And let me just say that I'd like this term to be about 5 ohms. Okay? I just picked 5 ohms, right? I want it to be smaller than RS because I know that if I go back to the original equation for F, this term contributes to the noise figure as RG over RS. So at 5 ohms, it's 10 times smaller than RS, so it should contribute very little to the noise figure. Okay? Now, given that, I can solve for GM. So I want a GM of 1 over 25 amps per volt, or about 40 milliamps per volt. Okay. And let me also observe that GM is 2 times IDS over VGS minus VT. So if I know VGS minus VT, I can also solve for IDS. So let me assume VGS minus VT, just to put a number in here, is 200 millivolts. And that gives me an IDS of 4 milliamps. Okay? So already you can see that in order to get the channel resistance to be small, I have to actually bias the device with substantial amount of current. All right? But 4 milliamps is reasonable. It's not low power, but for many applications it could be acceptable. All right? So now I know GM. I know RG. I know this, so I can calculate Fmin. So let's do it. So Fmin is 1 plus 2 times omega over omega t is 1 over 15. I'm operating at 5 gigahertz and my process is 75 gigahertz. GM is 1 over 25, RG is 5, and gamma over alpha is 2. Okay. So if I haven't made any errors here, oh, sorry, I have. Wrong equation. So it's RG divided by, sorry. I jumped ahead. First I should calculate RS opt. Okay, so RS opt is RG gamma over alpha GM times omega t over omega. So substituting RG is 5 ohms, gamma over alpha is 2, GM is 1 over 25, and omega t over omega is 15. So I get about 119 ohms for RS opt. Okay. Questions? Yes.
Fmin equation earlier, over which frequency did that equation hold? From DC to omega t, or?
Yeah, certainly not till omega t, right? Also, probably, if I had to give a conservative estimate, I would say omega t over 10, right? But you can probably use it up to omega t over 2, and it's reasonably valid. Okay?
Doesn't omega t depend on GM?
It does, yeah. Usually when you put the device in strong inversion, so we're making some simplifying assumptions here. Yeah. Okay, any other questions? Okay, well, what's interesting is if we calculate Fmin, which I was doing before, and somebody with a calculator should help me out here. So this is 2 divided by 15. GM is 1 over 25. RG is 5. And gamma of alpha is 2. So it's square root of, so it's roughly 3/5 here. So this is like 1.08. Okay, this is really low. Okay, this is a sub dB noise figure. Okay, if you calculate this in dB, I think it's like should be about half a dB or less. Okay, he has an ancient calculator with no log on it. Okay, so the point is that this is really phenomenal. If you could achieve a noise figure like this, it's just increasing, basically, that it's just hurting, it's like a 10% perturbation on our SNR as we go through this device. This is really great, right? If you could actually achieve this, you'd be very happy. Okay? Remember last lecture we looked at common gate device and we found the noise to be at least 3 to 4, factor of 3 to 4. Compare that here. Okay, really, this is good. There is a problem though. And let's see what that problem is. The problem is that we have to make our source 119 ohms. Okay, that's no big deal. I have a 50 ohm source. and I go through a matching network, and looking out here I see 119 ohms, and then I go into my transistor, and my transistor has CGS here and RG here, right? So RG is about 5 ohms, and CGS I can calculate from the omega t of the device. It's GM over omega t. So if I take 1 over omega CGS, then that gives me 1 over omega t times GM, which is 1 over 1/15 times 1/25, which is about 375 ohms. Okay? So this is minus J 375 ohms. So you can see that there's actually a pretty bad power match, right? If I just hook things up this way. It looks like I have a source of 119 ohms and a load that's minus J 375, real part 5. Right? This is a terrible power match. In fact, there's several reasons why it's not practical. First of all, you don't hook up the input directly to the antenna. You usually go through a filter. And that filter needs to be terminated with 50 ohms in order to work. What does the filter see? Well, the filter sees this impedance transformed down by the ratio of 119 over 50, which is about 2.4-ish. So looking into here, I see about 157 ohms, but minus J, capacitive. And of course, I'm assuming this is an ideal matching network that just transforms anything you give it. In reality, we know that the matching networks we design are used to match real impedances, right? So this is really an imaginary kind of calculation. But the point is that you're not seeing a power match. And so your filter is going to have more additional insertion loss, and you're going to lose a lot of signal because of this. So let's call this option 1. Okay, we get a great noise figure. But a terrible power match. Okay. Questions? Comments? Yes.
More current to achieve that high noise figure, so your power.
Well, but we already said we're going to burn 4 milliamps. We're happy. That's fine. I mean, that's a really good noise figure, right? If you could get that for 4 milliamps, you'd be pretty happy.
It's not very power efficient.
Yeah, if you take the power gain into account, it's terrible. That's the problem. Okay. All right. Well, let's try something else. Call this option 2. Option 2 is I still would like to get that great noise figure, but I'm going to put an inductor here to resonate out this capacitance. So this is minus J 375 ohms. I'll make this plus J 375. I still use a matching network, so I get 119 ohms, so I get that great noise figure. But now looking into here, I see 5 ohms at resonance, right? And this gets transformed down by a factor of 2.4 roughly. So looking into here now, I see 5 ohms divided by 2.4, or about 2 ohms. Okay. Well, have I really done anything better, right? This is just as bad. So again, I have a very bad match. The filter now sees 2 ohms instead of 50 ohms. And if you take into account the voltage divider, you're losing a lot of power, right? Most of the power is being reflected and not going into your transistor. Okay? Okay, well, let's not give up yet. Let's try something else. Let's try, instead of using a series resonant circuit, let's do a shunt resonant circuit. So I put an inductor in shunt with my transistor, and this is L prime, and then I use my matching network again. I still have 119 ohms here, and this is in the 50 ohm system. Well, remember, if you do if I put an inductor and shunt here, I can do a series to parallel transformation. So the equivalent parallel resistance seen here in resonance, so in resonance, it just looks like Q squared times 5 ohms, right? So the question is, what's the Q, right? The Q is just simply 375 divided by 5. But more generally, I can write the Q of the input device as approximately 1 over omega CGS times the R, which is 1/5 GM, neglecting the poly resistance. So this gives me 5 GM over omega CGS, or 5 times FT over F. So you can see that if you do a good job with layout, then the quality factor of the input network is actually quite large. In this case, I have a 75 gigahertz FT and I'm operating at 5 gigahertz. That means my Q is 75. That's an extremely large Q, right? First of all, you're not going to be able to find an inductor that has a Q better than 75. Right? Even if you go buy the most expensive inductors you can. So really what's going to happen is when you put this inductor down, you're going to add a lot of resistance in parallel, which is just basically increasing your noise figure. But also now notice that Q squared times 5 ohms is something like 30 kilo ohms. So it's in fact not really the right value either. Now it's a very large impedance. If I transform this down by a factor of 2.5, I still have something on the order of 10 kilo ohms. Very bad impedance match. 10 kilo ohms at RF doesn't really make sense anyway. It's way too high. Realistically, the board and the parasitics will limit the impedance to hundreds of ohms, right? So again, this is a really bad option. Okay. Questions up to here? Yes?
Why can't we just have two sets of matching networks? One for the noise figure and then one for the power?
How does that work? They need to go to the same matching network, right? Yeah. Hey, if you have a good idea, come talk to me. But as far as you can't get away with that. All right. Well, last lecture, you guys remember that we talked about bond wire inductance. The fact that, I should say bond wire and package inductance. If you ever build an LNA, even if it's on chip, it has to interface with the external world. Usually your antennas are not on chip. Say at a gigahertz, right, the wavelength's 10 centimeters, so even quarter wavelength is 2.5 centimeters, right? So at a gigahertz, you can't put an antenna on chip. It's just physically too large. So the antenna's got to be on the board or some external place. That means that you have to go from a board to a chip. And that interface, drawing it very crudely again, involves going through lots of parasitics. So here's my transistor input stage. And I want to connect this to ground on this side and to the signal on this other side. But realistically, because these pads, so these are pads, because these pads have to interface with an external world, especially here, this is a gate. This touches the gate. This is very electrostatic sensitive. Small voltage here can easily destroy this device. 10 volts will basically destroy this device. So I have to put ESD, a device which electrostatic discharge. If there's any static buildup on this node, it clamps it to ground and prevents it from going into this device. Okay? And then I have to house this chip. So this is my chip. This is the IC, integrated circuit chip. I have to basically put this into a package, and even this is not to scale. The package means that I have to use bond wires to connect from the pads to the package leads. There is a technology called chip on board where you actually directly bond to the board, but that's not as common. It's more common to go into a package. Okay? And so then this is my, you can think of this is where I connect up my source. So it has to drive these leads and then these bond wires and then the transistor itself. And if you see this loop, it's a physically large loop. And if you run a simple calculation, you can see that the electromagnetic the magnetic flux in this loop generates an EMF which is substantial. And in circuits, we model that by just putting inductors in series with these terminals. Okay? And these inductors are on the order of nanohenries. Okay? Now, there's lots of packaging technology to try to reduce these inductors. But at the end of the day, you're going to end up with, at best, hundreds of picohenries up to tens of nanohenries if you're in a really large package. Okay? So somebody clever realized that, hey, this is actually a good thing. I can absorb these inductors into my circuit and make my circuit better. So let's see how that's done. Okay? That's a question.
But before that, can I ask a question about option 2 and option 3?
Sure.
Can you combine option and option 3 by insert a small series inductor with capacitor and then put a big inductor in parallel?
Yeah, so basically you could do a multi-stage, right? So over here, I can have another matching network to try to match this up, right? So this is 5 ohms, and then I have another matching network to get to 50 ohms. But the problem is that all these components are in front of your amplifier, and any insertion loss adds dB for dB to your noise figure. So all of a sudden you have this complicated matching network, and instead of getting a noise figure of 1 dB, you're going to get a noise figure of 5 dB. Okay, I'm exaggerating, but it's gonna hurt you.
I think the problem in option 3 would be the capacitor so big that you want a high Q for the compensation. Then put a small inductor with series with those to reduce the capacitance. Then use option number 2 where I put the inductor in parallel with it.
Yeah, so you mean I could put a little inductor in series here, reduce the Q of this network. You can play games, right? And I'm sure, in fact, you're absolutely right. You can make this work. It's not going to be simple, but it's going to involve a couple stages, effectively, of matching. But at the end of the day, this is not what you have anyway. When you package it, you get these extra inductors. So the most popular way to do it is to use inductive degeneration. Okay. And the idea behind inductive degeneration is, let me just calculate. This is my voltage source. Let's call this LS CGS. This is GM V pi, or this is V pi. Let me just calculate the input impedance seen by this voltage source. Okay? So to do that, I can just write one loop equation. I'm going to go around this loop. And I could say that Vx is equal to Ix times 1 over j omega CGS plus Ix plus Gm V pi, and V pi is basically, again, Ix times 1 over j omega CGS, all times j omega Ls. Okay? And if I collect terms here, I have Ix 1 over j omega CGS plus j omega Ls. That's the second term here. And then the third term, you'll notice that the imaginary parts cancel out. J omega on the numerator, j omega on the denominator, they cancel out, and I get Gm Ls over CGS as a real impedance. So this is a real resistance. Now this is neat because there's no resistors in the circuit, right? Everything's basically L's and C's and this transconductor, and this feedback actually synthesizes a real resistance for me. Okay? Now that's really nice. That was the big problem with the MOS device, in that its input impedance had a very small real component. Now we can see that we can synthesize a large real component by just using the inductive degeneration that's there anyway, right? That's part of the package, parasitics anyway. Okay? So in other words, the equivalent circuit, so Rx, which is Vx over Ix, is an inductor in series with a capacitor in series with a resistor of value omega t times Ls. Okay? So the equivalent circuit looks like this. And it's important to note that this is not a physical resistor. And so it does not generate noise. The transistor is noisy, and we'll see later on how the transistor introduces noise. But you can't think of this as a physical resistor and say, ah, I just have noise associated with this. And because this is equal to the source resistance, the noise figure is at least 3 dB worse, right? If that were the case, this would be useless. We'd just lose all the good noise properties right away. Okay? Any questions? Yes, Debo.
So, like, because this LS is not a physical, you are not putting it separately, it's just a part of the bond wire. So while designing the circuit, how do you get an estimate of what will be LS?
Okay, that's a more complicated question. Usually you have to actually run electromagnetic simulation or do some simple calculations to figure out how big LS is. Because it really depends on the package size, the die size, the length of the bond wires, how bent they are. In fact, you can even go in with a screwdriver and play with that bond wire and change its value of the inductance. In many designs, you'll need more than a nanohenry to degenerate. You might need 3 nanohenries, in which case you absorb 1 nanohenry from the bond wire, and then externally you place enough inductance to get a match. Experimentally, you can try different inductors until you see a good input match. Okay. Other questions? Yes.
Is this for both BJTs and MOS, or is this?
Yeah, that's a great question. If you look at this equivalent circuit, it looks more or less the same for BJT and NMOS, right? Or PMOS for that matter. So this is really kind of a universal idea, and it's used for both bipolars and for MOS amplifiers. Okay, so let's look at the current gain of the degenerated device. Call this I out. Let me just calculate the current gain that I would see. And what I'd like to do is now form a full resonance. So coming back here, this does not necessarily resonate at the frequency of interest, right? So I could just add some inductance in series here, call this LG, and now move the resonance frequency, make this resonate at omega naught. Okay, so let me calculate the current gain under those conditions. So this is LG, this is LS, and then I hook up RS here, and this is VS. And I want to find the current gain of this circuit. Okay. So notice that by placing LG here, I've actually put my circuit in resonance, right? So the input current, IS, is simply VS over 2 times RS. Okay. Now that's approximate because there's also RG, but I'm assuming that RS is larger than RG. So the observation is that this is simply a series resonance circuit. If I hook up a voltage source here, right, these reactances in series cancel out and all the voltage appears across the real resistance. And the real resistance is this RS, right, and then the RS of the voltage source. And the output is simply the drain current, which is Gm times V pi. And V pi in this case is 1 over j omega CGS times IS. So if I write GM j omega CGS times, and then IS is VS over 2 RS, I can say that I out is capital GM times VS, where capital GM is simply minus J omega T over omega 1 over 2 RS. Okay. Now this is useful because now any input noise voltages in this loop get output referred by GM squared. Okay. So if I do a noise calculation, so let's start to look at the noise of the inductively degenerated MOS LNA. I can say that the output noise due to Vs is simply GM squared times Vs squared. And the output noise due to V gate is also the same thing, GM squared times V gate squared. So the question is, what about I drain? Okay. Remember before, I drain just simply flowed into the output. So let's draw a picture here of what's happening. So if I look at this current, and I'm just concerned with this current source, the drain noise, then by superposition, of course, I can set all the other noises to 0 and just focus on this noise source. Okay? So this is CGS. This is LS. Now it seems like this noise source just flows straight into the output, just like a common source device. But you can't neglect the contribution of this transconductance, because this current source will partly will flow into here and partly flow into here, right? There's a current divider. Division depends on the impedance seen in this branch relative to this branch. So the part that goes through here generates a voltage, right, which activates VGS, which activates this transconductance, which generates a noise. Now at this point it's not clear if that noise is going to be in phase or out of phase with this original current. But a little bit of more careful thought shows that if we assume that initially this current is going down, okay, and if that current flows here, it generates a negative VGS, right? And that would produce a current perhaps of opposite phase, which means that not the entire I drain will not flow to the output. Some of it will actually flow into this GM generator. Okay? Questions or comments? Yes? Yeah, exactly. So if you've taken 240, you understand exactly what we're talking about. Yes?
What is VG that you're using for I out or I0?
What's VG? What do you mean?
Or the second equation? Or
this?
Yeah.
So this is the noise on the gate side, right? This is just like before. There's a current gain, so if I come back here, if I have a noise source in this loop, it generates an output current, which is GM squared times the voltage, right? Okay, so let's analyze this problem a little bit more carefully. In fact, it turns out that for inductive degeneration, the result is pretty neat. Slightly different from a cascode device, if you've seen that before. Incidentally here, who has not taken 240 in this class? Okay. Oh, that's right. You have it for your homework. Great. Okay, some controversy. So pay attention. This will also help you on your homework, because you're going to do a similar analysis in your homework. All right. So what I'd like to do is calculate V pi for this circuit. And I've set all sources 0 except the drain noise. Okay? And for this analysis, instead of assuming this is a noise power, we actually assume it's a real signal and keep track of its phase, because phase is important here. All right? So V pi is equal to I drain plus GM V pi. These are the two currents flowing in, and then I have a current divider. So the current going in this branch is the impedance of this branch, j omega ls, divided by the sum of the impedances in both branches, which is j omega ls plus 1 over j omega cgs plus j omega lg plus rs. Okay? And this is basically the current that goes in times basically, let me make sure I got this right. So this is the current that goes here. Yeah, times 1 over j omega cgs produces a voltage V pi. Thank you. And there's a minus sign here, because this is inverted. Okay? Now there's some nice simplification that goes on. Well, this cancels out with this. That's okay. What about here? What is this and resonance? No, it's just RS, right? Because all these reactances just sum to 0 at resonance. And so you're just left with this term. So this, simplifying a bit, is minus GM V pi plus I drain LS over RS CGS. Okay. And so let me solve here for V pi. So this is also V pi. So I have V pi let me say 1 plus GM LS RS CGS is equal to minus I drain LS RS CGS. Okay? And you guys will recognize GM over CGS as omega t. Okay? So this is V pi 1 plus omega t LS over RS is minus I drain LS RS CGS. And what's omega t LS? That's RS, right? So by design, I select LS to satisfy this equation to give me an input match. So this gives me 2V pi, and let me multiply this by GM to give me the current through that transistor is minus ID GM over CGS LS over RS. And again, same thing here. This is omega t LS, which is equal to RS, so this is just minus I drain. So the interesting thing is that GMV pi is half of I drain. Okay, any questions? Yes?
So, like in the previous cases, we were doing something to find the optimal source resistance and then match it for noise. Here, we are not making any attempt. So, like
We'll do that. We'll do that.
So, first time we have already taken RS equal to omega t LS. Like it's a power match.
So what we're going to do is we're going to calculate the noise figure of the inductively degenerated device, okay? And then we can optimize it just like we did for the common source device. Okay. Okay, so now if you think about it, I know exactly all the noise contributions. I can now say that the total noise contribution is GM squared source noise, gate noise, plus drain noise minus drain noise over 2, right? RMS value. In other words, 1/4 of the RMS value of the drain noise ends up at the output. Okay, questions? Remember, the important point is that this current that comes back at you is correlated, perfectly correlated with this. And so they actually cancel each other out. They don't cancel completely, but it reduces the noise contribution. Okay, so now let's figure out the noise figure. F is, again, just like before, 1 plus gate noise, source noise, plus 1/4 drain noise divided by GM squared source noise. Okay, and again, we substitute. This is RG over RS. This is gamma over alpha times GM. This is going to be RS, this term here. And then for GM, recall that GM is 1 over 2 RS times omega t over omega. So if I square GM, I get omega t over omega squared, 1 over 4 RS squared. So here I substitute omega t over omega squared, 1 over 4 RS squared, and guess what? This 4 cancels out with this 4, and I end up with the same exact expression as for the undegenerated MOS amplifier. So this is the same equation as before. In other words, we got lucky. The fact that we degenerated our device produced a real input impedance, which is very convenient for matching, and it didn't increase the noise. Okay, that means that the F min of the device is exactly the same as before. So to answer your question, we don't need to redo the calculations. It's all the same. Yes?
How can I find the polarity of RP is in this direction? Like it's random tending in this direction and increase the noise.
Yeah, that's a good question. So let me go back and answer that question. So I'll repeat the question. The question is, how did you know that the noise was going to cancel it out? Why doesn't it add? Isn't the polarity random, right? The idea is that if I have one noise source here, right? And I'm interested in knowing the total noise drawn into my load, okay? Now what I've shown in this calculation is that if I assume that this is a deterministic current, then this current as deterministic quantity is always half of this current pushing in the opposite direction. So it would cancel it out, right? So now if I'm interested in the statistics of this signal, I know that no matter what, at any instant of time, whatever this current is completely correlated with this current, and it's in the opposite direction. Does that make sense? Yeah. Don't worry about it. Take 126. Okay.
So we're assuming that the noise is white, right? So it takes some finite time for the electron from ID to travel through the gate. And by the time it takes it back into effect, the current generated it should be uncorrelated to what ID is going to be.
Yeah. Actually, you're right. In a real transistor, the GM has a phase shift, right? Nothing in nature happens instantly. So there will be a slight decorrelation. And so instead of being 1/4, it's going to be slightly different. But for all practical purposes, at say ft over 10, ft over 5, the phase shift is very small. But it's actually a great question. And we'll see this actually happening when we look at a Cascode device. That phase shift is important. Okay. Now it turns out that I guess there'll be more. I'll hold off on that comment until we look at the Cascode device. Okay. All right. So let me kind of summarize what we have so far. So the summary is that if I take a transistor, inductively degenerate it, add a gate resistance, then I can make the real part of Zin equal to omega t Ls, and I could set that equal to Rs. And so I can have a power match. Okay? And the F min of the device is given basically by expression just derived. The important point is it's the same as the undegenerated MOS amplifier. And so it turns out that if you're willing to sweep things, basically you can play around with your device size and find the device size such that the optimum noise figure source resistance is also the same as the power match. So this allows you to achieve a power and a noise match. Okay? Now I'm not going to go through all the equations. You can do it analytically. It gets a little bit complicated. In the textbook, they go through a couple of design procedures, power-constrained design versus power-unconstrained design. The important point to take away, though, is that this degeneration allows you to achieve both Fmin and a good power match. Okay. Now, if you go back, if you actually now try to design one of these amplifiers, as I've shown here, let's say just driving a load, you'll find that it's actually quite a nightmare, because any real device has C-mu, right? And C-mu makes our device bilateral. And if I try to use a tuning network at the output to tune out the capacitance here, any change in the output load makes a change in the input load, and it gets very, very ugly. So almost everybody uses a Cascode device. So again, same architecture, inductively degenerated. And let's say I have a tuned output network. And this RL is either the next stage or it's the actual load. And I can also impedance match this, of course, to be the optimum load impedance. So this device is almost unilateral, and so it's easy to match both the input and the output for gain. Okay. So the question is, what about the noise of this Cascode device? Is this going to introduce more noise into our, LNA, right? We work so hard to make this a low noise device. Now we put another transistor there, and it has the potential of messing things up. Okay. Now, again, if you're naive about it, you would say, well, this has some drain noise, and that's going to get dumped into the output. So effectively, it looks like I'm going to be doing really bad. I'm going to take maybe 1/4 of the noise of this device, but maybe all the noise of this device, and put that into the output. And I would get a terrible noise figure. Well, that's not true, because this device, just like this device, is degenerated, right? This device is degenerated by this common source device, which looks a lot like a current source. Okay? So what I'd like to do is calculate the noise figure of a degenerated device. So this is RO, and I'd like to find basically the output noise of this device. Okay, and this calculation is very similar to what we just did for inductive degeneration. Okay, now this is basically our transistor in saturation. Okay, so let me draw the equivalent circuit here. We can very quickly analyze this problem because we've already seen it. This is the drain noise of the second device. This is I drain 2. This is GM V pi. This is V pi again. CGS. The gate is grounded, and I have a very large resistor here, RO. And in reality, I also have some cap. Okay. So let me assume that at low frequencies, all the current actually goes in this direction. Why is that? Well, because this is a very high output impedance, right? Let me assume that the output impedance here is much larger than the impedance here. Okay? Just a simplifying assumption. You guys can go home and do the full-blown analysis. In that case, V pi is GMV pi plus the drain current noise, these two noises, times 1 over j omega CGS. Okay? There is no current divider. All the current goes there. Okay? So a few lines of algebra, j omega CGS minus GM V pi is equal to I drain. And I can now solve for V pi. GM V pi is GM divided by minus GM minus j omega CGS times I drain. Or if I divide numerator and denominator by GM, I get minus 1 minus j omega over omega t. Okay? And so this is approximately minus I drain at low frequencies. So what I've just shown you guys is that if frequency omega is much less than omega t, this term goes away, this is minus 1, and therefore almost all the noise of this device flows through this GM generator. So this device contributes nearly no noise at all.
If the frequency is really lower than the omega t, then no current goes through CGS, all through goes.
That's a good point. Yeah. There's another way to look at it which explains that condition, but let's stick for this for the moment. Okay. There's a couple of interesting points about this perspective. This tells you that at really high frequencies, right, the amount of current that goes here is not necessarily all the current. Some of it will go through this capacitor, right? And as current goes through this capacitor, the amount of cancellation is reduced because this current will flow back into your load. So at really high frequencies, we'd like to minimize the capacitance on this node in order to minimize the noise contribution for this device. Okay? So coming back to here, we see that the cascode contributes a little bit of noise. Let's say at moderate frequencies. So that's pretty much, if you look at the workhorse CMOS LNA, it's basically what we've just seen. It's a inductively degenerated device. And the next question is, how do you actually build this inductor? So we said that you could use bond wires. You could also, so if this inductor needs to be larger than the bond wire inductance, you actually can realize this in many parts. So let me try to draw a layout here. So let's say this is my transistor. I can put part of LG on chip as a spiral inductor. Okay? LS and LG. And then this goes to a pad. And let me unfortunately have to draw over this. Then I have my bond wires. Let me draw it down here. And then I have my leads again. And I can actually then place a physical inductor here as well, if I want, and here. So the actual inductance has many parts. There's the bond wire portion. There's the on-chip portion. There's the package leads. And then there's maybe board inductors that we use. Okay. Now from a design manufacturing perspective, this may seem a little bit like a nightmare, right? Because these bond wires can vary, their lengths can vary. Traces on the board, the amount of inductance you pick up can vary depending on the board height, the distance to the ground plane. Essentially on the board, the traces look like transmission lines if you do it right. And so this topology requires a lot of fine-tuning in order to get the matching right. Another option is to build this amplifier differentially. So let's look at that and why that helps. So a differential version of this amplifier looks something like this. Again, we're going to use a cascode topology. We're going to use some on-chip inductors as the load. And I can use some on-chip inductors for the gate here. And then this is going to come to a couple of pads. And this here goes to ground. So this is the total inductance to ground. Now the nice thing about a differential version of the LNA is the inductance on the source side here, on the coupled source side, doesn't matter because on chip this is a virtual ground. And if I want to degenerate these devices, I would actually just put physical inductors in the layout. So these would be on-chip inductors. And the nice thing about on-chip inductors is that they're very accurate. Their values can be very precise. It just depends on layout, and the layout just depends on basically this. So on-chip inductors are usually spiral inductors, are very accurate. Let's say on the order of 3%. And that's because the way we build these inductors is we build either square spirals or polygon spirals. It has to be a planar structure, so we have to make it in a plane. But the inductance is more or less a function of this dimension, right? Let's say the length, the width of the conductors, the spacing of the conductors. And these are very well controlled in an integrated circuit process. And that's why the inductance value is so accurate. So I can synthesize a very accurate degeneration inductance here and synthesize a very accurate real component of the input impedance with a differential topology. And these additional inductances are all on the gate. And those I can use basically to fine-tune the frequency. So this differential topology has a big advantage in that I can easily just change the gate inductance on the board. So this is the board, let's say, contribution, to get an input match and not worry about messing up my 50 ohm input match. Okay. Now you may say, well, this is differential. Isn't that a problem? A few years ago this was a problem, but nowadays it's actually fairly common to find filters that are differential. So if you're building a system, your antenna is usually single-ended, okay? Although that's not necessarily a requirement. You go through a filter. This is a SAW filter, and its output is differential. So you're in business. Then you put in these gate inductances externally to get the match, and then you go differential on chip. And the beauty is that now the path is very well controlled. And let me explain why. So this is the path that you care about. All the current basically will flow in this loop and come out. And you can have very fine control, basically you can, with layout, where this current goes. On the other hand, ground is a little bit scary because lots of things are grounded, right? All the transistors, their bodies may be grounded. You might have multiple ground pins on a package. So if you're not careful, your ground current may take a path that's very different than you intended. So in the case of a single-ended design, if you know what you're doing, you will carefully ground the input stage separately from everything else and make sure you control that path. But if you're not careful and you share that ground, you actually don't even know what path the return current is going to take. Okay, so that's the advantage of going differential. Now there's of course other advantages of going differential, which you've learned about in other classes. Differential amplifiers have good power supply rejection. They have good immunity to any common mode signal that's picked up. So any kind of substrate noise that's picked up in common, let's say from a digital stage of your design, will get rejected by the common mode rejection ratio of this amplifier. So going differential has other benefits as well. One thing that you guys have learned about is differential amplifiers have much lower IP2, right? So differential amplifiers have ideally 0 second order distortion. Otherwise, it's matching limited. And that was a bonus problem for you guys. Nevertheless, if we make these transistors fairly large and we're careful about our layout, we can get pretty good matching and therefore very good IP2. Subramanian?
Wouldn't you have to match the bond wires also now? Or is that not a problem?
You'd have to place them right next to each other and be pretty careful. Yeah. It requires a balance, right? But at the end of the day, you can do a good job. And having a good IP2 means that this is very good for direct conversion, right? We haven't talked too much about architecture in this class, but we know a direct conversion receiver is one that takes a signal and converts it down to DC. We've also learned that any even order distortion generates DC. So if this amplifier has even order distortion, it will generate distortion right in band. And by making it differential, effectively we're making that distortion very small. Okay? Questions or comments? Okay. And as we pointed out earlier, almost everything we've said today applies also to bipolar LNA design. Very similar.
So like going back to why bipolar, like someone pointed whether the same model is applicable, but bipolar also have a real component of input impedance.
The R-pi.
Yeah, so doesn't that make a difference, because options 1, 2 that we talked about had difficulties mainly because our RG was very small.
Yeah, in a bipolar design, if you're at a frequency, let's say FT over 10, and your beta is reasonable, let's say about 100, the input impedance is more or less capacitive, 10 times more capacitive than resistive. Okay? So the beta roll-off, right, is beta times lower than the FT frequency. So you can see that the real component starts going away very quickly. So effectively, if you're using a bipolar transistor, let's say FT over 10, forget the real part. It's not going to make a contribution. All right. Other questions? Okay. See you guys next week.